So I'm going to present you some work that we have been doing for the last about 2 years, and some of the recent results that actually we have got in collaboration with people at NIST at UMD, people at UMD in different groups, and people at UMBC for the theoretical part. And here what I'm going to show you is our work on two-dimensional frequency comp, in more particularly the interaction between the CW wave and the soliton. And actually here I try to be fancy, showing like a microchip, because that's basically the only place where you're going to see a microchip. I mean, all the things I'm going to show you are actually totally independent on the type of resonator you're using. It's just we have some, so we're using this kind of thing. So just bear that in mind. So before actually going into all the physics and all that, I'm going to actually just quick reminder. I guess everybody is familiar with what's frequency comp, what's a soliton. So it's going to be very quick how we get dissipative Kerr soliton. So first we take microring resonator, inject light on resonance. So like this, we can get light into the resonator. If you inject enough power, you're going to get the modulation of the refractive index through cell phase modulation. If you are in the correct dispersion, which is anomalous for soft excitation, you're going to get modulation stability. And if you're lucky enough, and when I speak about luck here, most of the time that's actually luck, you'll get a soliton, which is a single pulse that travels throughout the resonator. That doesn't mean you have a frequency comp yet. Here you have a single, this is actually called soliton, but to get a soliton, a frequency comp, sorry, you actually need to extract it periodically into the waveguide. And you're going to get a pulse train, and that's actually what's going to get you the frequency comp. And here it's important to notice that what you're actually measuring here is not exactly the state that you have in the resonator, that's what you extract at every round trip. And because of Fourier transform, at the input you get a nice CW, it's a CW light. And because you have the pulse train, you Fourier transform that, you get a frequency comp. So frequency comp are pretty awesome for a lot of reasons, and one in particular is because it's frequency division. So I totally stole that from Scott Didams and made a little video out of it. The frequency comp is the frequency division between optical frequency and the repetition rate in the microwave domain. But you can go back and forth. So that means if you have a stable optical frequency, you can get a stable repetition rate in the microwave and vice versa. And so that means you can have a lot of application for dissipative Kerr soliton frequency comp. And I stole that from Tobias Kippenberg. I'm stealing a lot of figure at first, you'll see. They're going to be like original work, all right. In particular at NIST, the S stands for standards. We care about metrology application. What that means we focus a lot on optical frequency synthesizer and optical atomic clock. For this kind of work, we need to fully stabilize and self-stabilize the frequency comp. To do that, you need an octave bandwidth. And that's why actually we work with these tiny rings, these tiny chips that I show in the first slide, is because for power consideration, you want to minimize the number of comptis you have in your octave. So that means you need to work with a large rep rate. In our case, we work with a small ring radius of 23 micron in silicon nitride, and that gives you 1 terahertz of repetition rate. And like I say, everything that I'm going to show you is totally independent from this repetition rate. But it really made our life much easier to have this huge repetition rate that we can resolve optically. So why is it really challenging to actually get this octave spanning frequency comp and self-stabilization? It's because there's not many way actually to self-stabilize a frequency comp. You need to do F to F. And if you take one comp tooth, you double it through SAG and beat it against its harmonic, as you can see through the very quick math here, you actually get the frequency of the carrier envelope offset. Issue is like, there's really not a lot of power at this frequency because you have the intrinsic hyperbolic square envelope of the frequency comp that's going to limit the power that you have at the frequency of interest. And there's a trick that has been found now, like it's almost like a decade, where you can introduce dispersive waves using higher order dispersion of your resonator, where your comp is actually going to be resonance. And you're going to have resonance enhancement at a given mode. If you tailor your dispersion correctly enough, you will actually have this resonance enhancement at harmonic frequency, so you can do F to F. And so far, to my knowledge, that's the only way you actually get a coherent octave spanning frequency comp. That's actually not enough. So I mean, even if you get enhancement, let's say, of like multiple tenths of dB, you still have like minus 30 dBm of power. If you think about second harmonic generation, you get like 10 dB of losses. You try to double that, beat it against here, you will not measure anything. So how we actually, most of the time, do stabilization is use an auxiliary laser, as shown in this red line, that you actually come and lock to your frequency comp. This laser has a lot of power, can double as much as you want, and you're going to beat it and actually retrieve your carrier envelope offset. Well, the issue is like you have this other laser that it's a degree of freedom, and you're not really doing anything else than locking it to your soliton. So the question is like, can we actually use it in a better way? And so the question is like, can you actually use it in a better way, which means can you actually send it to your resonator? And the answer is pretty straightforward, that's yes. And at least in our group, everything that spurred all our work is really this work by Pascal at Deleuze's group, where they actually send a second laser into the resonator, and they have seen a spectral extension of the frequency comb up to the secondary pump. And that's kind of like a groundbreaking work, because that means all of a sudden you're not limited by a public second square envelope. You can have almost unlimited power wherever you want in your secondary, in your frequency comb because of your secondary pump. What we have done actually like use one of their features that they show in their paper but didn't exploit to show that you can actually create new type of dispersive wave on demand because of the secondary pump that you're sending to your resonator, and you can obtain a record-breaking 1.5 octave of coherent frequency comb. But the issue is that even if it's a coherent frequency comb, doesn't mean it's a frequency comb that you can use for metrology. Because here, okay, we show like a huge frequency comb, so that means we kind of solve the issue of stabilization, and basically my work here is done, right? If you look closer at the frequency comb that you obtain here, you actually can zoom in, and what you will see is actually two spectral components. And what is really interesting is that both components exactly have the same repetition rate, but there is this offset that we used to call the stitching back in the day, that we call delta F, between the translated portion and the primary portion of your frequency comb. What does that mean? That means you actually have a degree of freedom that you still need to lock. What is related to this stitching is actually what we have noticed, like there's a really obvious trend between the integrated dispersion at the secondary pump and this offset of frequency. And so we concluded that because your frequency comb is not on resonance, because it's dispersion-less, so that means the repetition rate is the same across your whole bandwidth, your cavity has a dispersion. That means your cavity resonance is going to move. So that means when you pump, there's going to be a natural offset between the cavity mode and your frequency and your comb, the nearest comb tooth, which actually is the integrated dispersion at the secondary pump. That's actually this value. So that's why this offset naturally occurs because of the dispersionless nature of the frequency comb and the dispersion nature of your cavity frequency. And like I said, it's still another degree of freedom. That means like for metrology purpose, we have solved absolutely nothing, because it's totally not different from locking an external laser to your frequency comb or sending it into your resonator and having another frequency to lock. You still have to lock something. But that means we have another degree of freedom, and in optics that's pretty nice, because when you have another degree of freedom, usually you can harness it and do nonlinear optics with it. And so I'm going to show you that actually you can harness this frequency offset to actually do nonlinear optics and create a 2D comb. So to start first, just a recap of like what you get as a frequency comb. You have this pulse train, and it's really important to recall that most of the time we only work with the envelope. That means that it's really nice hyperbolic second, but there's a fast oscillation under. And if you're familiar with the work of Ted Hench, Natalie Piquet, you will recognize this figure because they always show this kind of like phase between the fast oscillation and the envelope that increase at every pulse train. And that actually is the origin of your carrier envelope offset, right? What happens in a resonator, these pulses are actually a snapshot at every round trip when you extract your soliton from the resonator. So that means actually what's happening in the resonator, you have a group velocity that is different from the phase velocity. And because it's different, the oscillation under the envelope are drifting by a fixed amount at every round trip. So now we can actually look at what's inside the resonator instead of what's in the waveguide. So we can actually work in the referentials that freeze the soliton. It has a fixed repetition rate, so we can introduce this phi, that is the angular angle, the angle of the resonator theta minus the repetition rate over time, which means the envelope is effectively frozen. That means you can look at any time possible, it's always going to be there. But because the group velocity is different from the phase velocity, the phase oscillation is going to drift. So if you take a fixed point in phi, which is a fixed point in the azimuthal angle, what's going to happen with time, you can see that they're going to oscillate. If you record it in time, they're all going to oscillate kind of differently, but what's really important is that this period is exactly the same. It is relative to the discrepancy between group velocity and phase velocity. If you have a signal in time, you can Fourier transform it, you get a single frequency. So effectively, what does that mean? That means a single soliton in a cavity, or actually a single soliton that propagates into a fiber, can be recasted as a single frequency. And if you want to dig deeper, I invite you to look at FADIV, work from FADIV from the 70s, and action angle variable and all this stuff. If you understand it, just tell me, because I still don't. And just trust our collaborator, Cornelis Menuik, that came up with all this stuff. He's a theorist. So that means like now we assume that a single soliton in the cavity is actually a single frequency. When you inject another laser, what happens is you're going to have like a binding of the group velocity with the soliton. And that's a very nice work that has been shown by Stuart Murdoch in New Zealand, where actually they show that what you send actually as a CW wave externally, but he grip the tail of the soliton and become essentially a dispersing wave. So what that means actually your external laser in blue here going to travel at the exact same group velocity than the soliton. It has been shown actually recently through some other spectral extension work that it's actually exactly the case, that every component travels at the same group velocity. So that means that we can still assume the little cartoon that I showed earlier about the same group velocity and actually freezing your pulse in the resonator. So now that we know that we can freeze every component into the resonator, we can start looking at the integrated dispersion. So integrated dispersion, if you're not familiar, that's basically account for the cavity resonance offset from a fixed grid of resonance. So if you have your main pump here and you inject your secondary pump here, what's going to happen is exactly the same as if you have like your frequency comb that is like this red line, and you're going to get an offset that is over here. So that means you have introduced an offset of carrier envelope offset here. So it's delta FCO. If you recall the couple slides above, what I show you is like the carrier envelope offset is essentially a shift of phase velocity. So what you have done here, you have actually exactly the same group velocity in your resonator. That's what has been shown in previous work. But you have introduced a shift of phase velocity. What does that mean? You have like one frequency, that is the soliton, another frequency, that is your secondary laser. We're in a nonlinear system, right? So like pretty easily, you can mix it. Here you have an OPO type system, where instead of a CW wave, you have actually your DKS, that is a single frequency that acts as a pump. You have your secondary pump that I call SP, create an idler exactly at the delta omega from the secondary pump. So that's pretty cool, but actually these frequencies are not exactly single frequencies, right? They do have azimuthal components. So that means this frequency here is actually like the soliton. This one is kind of like a CW wave-ish type of system, which means this one's gonna become also a CW wave-ish type of stuff. Here that's like not totally random what I drew. It's actually like if you run the simulation, that's kind of like what it looks like, which means that they will have different azimuthal components. So that means here, intrinsically, what you have is you have two dimensions. You have the first one that you're kind of used to, the azimuthal component, that's what we observe experimentally, right? But you also have the second one that we actually always play with because we tend to log the carrier envelope offset. So actually, we always use this second order, this second dimension, just we never harness it for nonlinear optics. And in this case, actually, by sending your secondary pump, you can actually harness it and do some mixing in this phase velocity space. So that's pretty cool. I show you everything that happened in the resonator. We don't actually see what's in the resonator. We see what's in the waveguide. So here you have three frequencies in the phase velocity. So that means you have three phase velocities. So that means you have three carrier envelope offsets. As you recall, this discrepancy of phase velocity, group velocity yield a carrier envelope offset, which means like each of these single tone in the phase velocity will each yield a different carrier envelope offset, which means this one's going to create frequency comb here, this one offsetted by the quantity delta omega, and this one offsetted by a quantity minus delta omega. So it's kind of nasty when you do experiments this way. It's kind of always nasty. You have like all these components everywhere. It's not very nice. So like another better way actually to recast what you're seeing, and I'm going to show that everywhere. So it's kind of important that this thing gets through, is that you can actually account for the fact that each azimuthal mode number is every component that are between minus f rep over 2 and plus f rep over 2. So that means like if you take one comptus, every power that in between in this bracket is actually the same azimuthal mode number. What that means if you take the pump here, you can plug in this kind of like 3D space where you have like in x-axis the azimuthal mode number, in y-axis this like minus f rep over 2, f rep over 2. Obviously, the pump is centered in this thing because we normalize it to the f rep of the frequency comp. So it's going to be 0, 0. All the frequency, all the tone of the DKS are actually centered in mu, so they're all going to be at 0 in omega with different mu, right? But this guy over there, it has a shift of minus delta omega, right? So that means for each of the mu number where there is actually power, you're going to actually shift it of minus delta omega. If you do a very nice early simulation, and here that's a single early simulation where you actually recreate the experiment, I'm going to discuss that in more detail later, you can actually see very well that you have like one component that is at 0 FCO, normalized 0 FCO, and you have two other components that are spaced by this delta omega in FCO, and basically you show that you have like this nonlinearity in this phase dimension. So here I just pick a particular nonlinear interaction. What you can see is like, well, all the Fourier mixing possible are basically at reach, right? So how to model the design? And this thing you can basically kind of trust what I'm showing because I didn't come up with. It's Curtis Menuik that you can trust much more than me. So on one hand, to model the system, it's very well known. You can either do coupled mode theory, or on the other hand, do the Lugia-Lefevre equations. They are totally equivalent as one is in the mode domain, the other in the time domain. On the linear part, they're the same. Loss, detuning, dispersion, same. On the nonlinear part, they are not. In one hand, you have mode mixing, conserving the momentum. On the other side, you actually self-phase modulation. Which means, in one hand, you actually need to like account for every possibility possible in the mode dimension. On the other hand, it's actually super easy. You just account for self-phase modulations that shrink or expand your poles, and it's kind of like going to be automatic. So in our system, we're actually in between, right? You do have like this pulse that is very nice for the early, but you have this mode mixing that is very nice for the coupled mode theory. So the answer is coupled Lugia-Lefevre equation. So here what you will see is that instead of having just A, as in the Lugia-Lefevre equation, you're going to have the subscript sigma that account for all the different modes in the phase velocity when you introduce a secondary laser. And you're going to have the sum over all the phase match component. And you're going to introduce a dispersion-less term that accounts for the phase shift of each of the components. There's a lot of simplification here. It's not just like you can merge them both, because this equation is actually not true all the time. It's only true when you have a soliton, because the modulation instability doesn't produce a single tone in the phase velocity. And for this equation to exist, you need that. So that means you can only have this kind of equation when a soliton already exists, which makes it kind of more complicated. So to start first, we're going to show you that actually the integrated dispersion is what caused the shift of phase velocity. So we take a microring resonator, 1 terahertz, and we measure the dispersion across from 1610 to 920. And that fits very well with the simulation that we can do in COMSOL. And then we take a dissipative kersoliton, and here it's important, and there was a huge pain to be honest, it's the same exact dissipative kersoliton, where we actually change the secondary pump across all the modes that we have access with our laser. And actually, if you just look at the dispersive wave and we zoom over it, you will see that the dispersive wave of the primary soliton is actually not moving, stay at this 0 normalized. But all the different components of the secondary pump are actually moving. And that follows very well the integrated dispersion that we just measured. So what essentially it is, that means like the integrated dispersion is a measurement of the shift of frequency carrier offset when you're in a dual pump system, which means also measure your shift of phase velocity. Great. So now I show you that if you inject a secondary pump, you know that the integrated dispersion is going to define your shift, and essentially is your frequency spacing in the phase velocity stuff. So now I can show you that we can do an OPA system. So I send a secondary pump here. Kind of forgot to put which mode number it is, so it's like 91, 92, 93, 94. And we have the single pump here, the single pump DKS that is here, and always the same. And we get new idler. Here you can see there is new dispersive waves that are based on phase matching. I'm not going to describe it in detail, but if you have any questions, don't hesitate. If we zoom across this thing, you can see as expected here, for the different pumped mode, we're going to have like a different offset, frequency offset. In this case here, we're limited by the resolution of the OSA, but the same thing, you can see like the increase of the frequency offset in the other dimension. We can recast it in this 3D plot that I presented you earlier. So that's experimental data, where you can see the signal is pretty well offset from the primary comp. It's very easy to see that, and the idler is actually offsetted in a negative sign from the DKS. So to kind of like have a better idea of like what's happening actually in the phase velocity mixing, we can look at the carrier envelope offset as essentially they're almost the same. So we can integrate our comb over the mode number mu, and so basically you just do a sub over mu. And you get this very nice plot where you can see that you have your DKS acting as a pump, so this one is never moving. You have your signals that we tune, and we get the idlers that follow exactly the frequency offset, just opposite sign from the signal. So that's a demonstration that you have an OPO in the phase dimension of your frequency comb and introduce another dimension that is not the azimuthal mode number. We can do an elderly, so that's actually like an equation that's been introduced by Hossein Taheri in his, it's a very nice paper, where you can just introduce like another driving force based on like the mode that you're pumping and the integrated dispersion where you send it. And if you reproduce exactly the experiment, which means you're not only simulating the elderly, but you're actually extracting your soliton at every round trip, you recreate your pulse train, then you FFT it. That's the kind of comb that you get. So it's kind of different from like the, you know, kind of like easy LLEs that you can get and just get the envelope, you FFT it, and that gets your envelope of the comb. Here, that's actually like the comb teeth are not just by like doing like a stem plot of MATLAB, right? That's actually the type of like result that you get. And so you can zoom and actually see the offset in FCEO that are of opposite sign as we see in experiment, and you can reproduce the 3D plot and the OPO in the phase velocity, the carrier envelope offset domain. Great. So I show you that basically we can have an OPA in this thing. I show you also that it validates the couple LLE equation through this kind of like full array that account for everything. So now, can we actually cascade an OPO? So as you're all familiar with it, like how to get a frequency comb, it's crazy. You almost always get a primary OPO, which then cascade into all these different comps. So can we do that instead of doing in mu actually in this phase velocity system? To do that, we take another resonator with another dispersion. And as you can see, when you single pump it or dual pump it, the spectra is quite different. Actually, if you zoom at all the different comps, you can see that you do not get only one offset, but you get several offsets. And actually, if you look at all the different components that you have like many more than just 2 or 3. Can project it again in this 3D plot. As you can see, you have many comps. And that's basically a 2D comp in both the mode number and this phase velocity dimension, which is a frequency carrier offset. Reproduce it with the LLE again, and if actually we do the integral over mu, you can see that the LLE and the experiment match very well. So I'm kind of like fooling you actually right now, because I'm telling you that it's a 2D comp. It's not really a 2D comp, right? Because if you go back, like, you can tell me, well, but in mu they don't really overlap, right? That means you have like a nice cascading in that direction, you have a nice comp in that direction, but it's not a 2D comp because there's no overlap. For instance, like the sigma over 0 and the sigma over 3 actually you can never get the bidding between them two. So one way to do that is like you can actually try to reduce this omega repetition rate, the repetition rate in the phase velocity dimension. Well, it's pretty easy to actually get the smallest possible because that means like where the dispersive wave is, right? That's literally when integrated dispersion is closest to 0. So that's what we do. We pump here at the dispersive wave. As you can see, dispersive wave of a single pump DKS is over here. We pump it, and actually not much happened. It was really underwhelming when we got this result because basically you don't resolve anything. You don't see any fun stuff happening because we cannot resolve anything because here omega is technically 0, right? Omega is not 0. It's actually 1 gigahertz something. And if you send your whole comb actually into a photodetector, what you will see is like equispaced tone that are actually separated by 1 gigahertz. And because I showed you earlier that actually like this cascading, we can resolve it optically, that's not nonlinearity in our photodetector, right? You can do the simulation, and actually the simulation show you that you have a very nice 2D comb with very nice, basically you can resolve every comp T either in mu or in this omega dimension. And here I can show you like in the simulation that we get about like 10 comp Ts, and you can probably go much higher than only 10 comp Ts. So that's the demonstration of a 2D comp. So that's the conclusion for the first talk. So I hope in this first talk, at least, I convince you that the Karem of set is not just a parameter to lock. So we always play with it, and we kind of dismiss it most of the time. And we can actually do stuff with it. We can actually play with it to do nonlinear optics. And I discussed with you a model that accounts for the nonlinearity of both azimuthal and phase dimension. That's still something that we're working on to actually show the copolarity can work. I'll show you multiple ways to create a composite frequency comp, and that you can actually cascade nonlinearity in this phase velocity dimension to create a two-dimensional frequency comp. So what's next? So there's a lot of things we're hoping to do with that, and in particular is that's the kind of gear that I show you in the first slide that I stole from Scott Dillams, is can we actually introduce another gear using this other frequency repetition rate. If you remember also the very first slide, I told you that the repetition rate of our ring is 1 terahertz. The repetition rate in this frequency here is 1 gigahertz. That means we have 3 orders of magnitude difference between the different repetition rates. So can we actually introduce another wheel in this kind of like frequency division scheme to actually then convert even further? And the last question is actually, right now I told you that these 2 dimensions are orthogonal. It's still a question. Are they actually orthogonal, or actually one impacts the other, and actually can we have a discrepancy between them two? And that's something that we're still working on. And with that, I'd like to thank everybody that worked on it. So from Scardy's group, Jordan, Michael, and Christy, Jan Chambos, that is at UMD and helped us a lot, Avik Jude, that is now at UMD, helped us a lot, and Curtis Menuik and Prajat that are working on the theory side. And with that, I'd like to thank you.